The problem statement from GATE Physics 2014 reads as follows. The input given to an ideal op-amp integrator circuit is, it has been given as a step function. The correct output of the integrator circuit is. Before we start solving this problem, we need to first understand what an integrator circuit looks like. So this is a circuit diagram for an integrator circuit using op-amp. Before we solve this problem, we first need to ask ourselves a few questions. First, whether the op-amp in this given circuit is ideal or not. It is ideal because the question itself says so explicitly. So yes. Even if the question were not saying it to be ideal, we'll assume to be ideal unless the question explicitly mentions that it's non-ideal. So usually in your problems, we'll see that it is an ideal op-amp that we can come across. If it's non-ideal, it has to be explicitly mentioned. Second, we'll check if there is any feedback in this circuit or not. So how do we check that? We check that by tracing the output and see if it's connected to an input or not. So this is the output node and it is connected to an input using this feedback circuit. In this case, the feedback circuit consists of a simple capacitor. So the answer is yes, there is a feedback. Now the next question is what kind of feedback? So since the output node is connected to the inverting terminal or the negative terminal, we call such a feedback negative feedback. Okay. Now, since this is an ideal op-amp, the current going into the inputs of both the inverting and non-inverting terminal would be 0. And recall, we had mentioned that there is an R in input impedance. Usually this R in input impedance is very high. But let's apply Ohm's law across this impedance. So I can write V plus minus V minus equal to I times R in. Now, since there is no current flowing into the op-amp, so I can write V plus minus V minus equal to 0. This gives V plus equal to V minus. This condition is called a virtual short. Why short? Because plus and minus, the inverting and non-inverting terminal are sitting at the same potential. Why virtual? Because there is no physical short. There is no wire that's connecting these two terminals. It is just the peculiarity of the op-amp that these two happen to be sitting at the same potential, and we denote it by using a dotted line, a straight line which is dotted, to denote that these two terminals are virtually shorted. Now we'll use this information to solve this integrator circuit. So I've replicated the circuit here, and so remember that this is a virtual short. So this potential, let's name this node Vx. So Vx is equal to 0. Remember that. And also no current is flowing into the op-amp. Let's assume a current I is flowing through this resistor, and if a current I is flowing through the resistor, the whole current will have to flow through the capacitor also, because no current can go into or out of the ideal op-amp. Okay, now let's apply first Ohm's law across the resistor R. We can simply write V in minus Vx equal to current flowing through the resistor is I and the value of resistor is R. So this will give V in, since Vx is 0, so V in minus 0 equal to IR. This implies I equal to V in over R. Let's call this expression 1. Now across the capacitor C, we can write the expression current flowing through the capacitor equal to C dV over dt. This is a general expression for any current flowing through the capacitor. Now look at this capacitor. The current flowing through this is I is equal to C dV. V is the potential difference across the capacitor. In this case, it's Vx minus V naught. Vx minus V naught over dt. Since Vx is 0, I can simply write dV 0 minus V naught over dt. This implies this expression comes out to be minus C dV naught over dt. Now what I am going to do is I am going to equate 1 and 2, because both are the expressions of current I. So I can simply say V in by R is equal to minus C dV naught over dt, and I'll just bring the dV naught term here. So I'll say dV naught equal to minus 1 by RC V in dt. Now if I integrate on both sides, so I can simply say dV naught, that's V naught, equal to minus 1 by RC V in dt. Look at this expression now. What are we seeing here is that in order to obtain output voltage, we'll have to integrate the input voltage, obviously given some limits, but output voltage can only be obtained once you integrate the input signal. Hence, such a circuit is called integrator circuit. Recall that we had talked that operational amplifier is used to is used to create some mathematical operation. So this is just some example, the integrator, right? So now if we go back to our question, we were given that the input waveform looks something like this. So this is V in, this is your time, and the input waveform, I'll use a different color. So the input waveform looks something like this. It's a step function, so it looks like this. So this time is t naught. Okay, all right. So yeah, so this is, and now we are required to find out that how does the V output waveform looks like. So let's do this. This is time t, and this is the same time t naught. Okay, so now let's integrate. So we need to find how does V naught look. Now we know that V naught is nothing but integration of V in with respect to time. So let's say from time, let's say case 1, from t equal to 0 to t equal to t naught, how will it look like? So I'll simply say V naught equal to minus 1 by RC V in dt. Now V in is 0 between, look at that, between 0 to t naught, V in is 0. So it will be minus 1 by RC 0 times dt, which is nothing but 0. So V output, now I have assumed that at time t equal to 0, the output signal was already 0. Otherwise there will be an offset, which will not impact us. So for the sake of simplicity, I have assumed it to be 0. So this will be 0. Okay. Now let's see what happens for case 2 for t greater than equal to t naught. Let's do this expression now. So again, V naught is minus 1 by RC V in dt. From now the limits are t naught to t, and accordingly the value of V naught here will be the value of V naught at any given time t minus value of V naught at time t naught. So this can be written as minus 1 by RC. The value of V in, let's assume this level to be some, what should we do? Let's call this some level V1. Okay, this is a constant, it will come out minus V1 dt. So this expression will come out to be V naught t. Now V naught t naught is 0. At time t equal to t naught, the value of V naught is 0. So V naught t minus 0 equal to minus 1 by RC V1 times t minus t naught, right? So note that at time t equal to t naught, the value of V naught will come out to be 0, which is what we expect since this is a continuous function. So it will be 0. However, from this time onwards, it will be a negative slope. Note that the coefficient of t is negative. So it will be a negative slope. something like this. So that's how the output of V0, the output waveform, will look something like this for this given input waveform. Let's see which options do we match. Okay. Yeah, so what we were getting is, remember what we were getting is like something like this. So it looks like none of the options are matching. So yeah, that's it. No option is correct as far as this question is concerned. Okay, thank you for listening.